left yesterday, so assuming that you remember the thing that I showed about the disturbing function and the Hamiltonian formulas and so on, we're moving into something that we like to call application. In a sense, I'm going to try to spend some time on secular theory and some time on resonant problems, both for the asteroids and the satellite, if I have enough time. Now, I cannot resist, though, to go back a little bit to show one plot, just to say something about what Andrea was saying before. And remember I showed you this plot yesterday about asteroids coming to the near-Earth space from the 2 to 1 mean-motion resonance with Jupiter. And what I don't show in this plot, I should have put it also, is that this is, for example, in a conservative model, no Yarkovsky. And very few objects can go past the 5 to 2 resonance here. If you include the Yarkovsky, given enough time, because this is several hundred million years, there are objects that reach near the 2 astronomical units limit, actually. So you have a better chance of moving objects even from the 2 to 1 resonance to the near space. If you have the
I think the proportion is 80% to 20% of
yes.
retrograde versus direct.
Yes.
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 A very strong effect.
So, yeah, I'll start from that. So remember what is the disturbing function for the problem of the asteroids, which is this type of Fourier expansion. And among these arguments, all integers satisfying the D'Alembert rules are possible. And of course, there are combinations which do not contain at all the mean longitudes of the asteroid and Jupiter or any perturbing planet. And these are the secular terms. So if one is interested not in the exact orbital motion of the body on its orbit, but only on the long-term change of the orbit, the secular precession of the orbit, he can look only on these secular terms. So one way of doing it is I say I invoke the averaging principle. I think that the short terms are not important if there is no resonance satisfied. Of course, resonances are dense in phase space, but the order of the resonant model, as it increases, it diminishes the strength of the resonance. But let's say you can do it. If you just kill these terms and work on the secular terms, you're solving a problem which is close to the original one, but not exactly. Now, in principle, there is a better way of doing this job, which is a canonical derivation of the other Hamiltonian. And basically, it means that you write down the least series, let's say up to order 2, in the small parameter, in the mass of the perturbing planet, and then you specify what you want to do. You need a generating function for the transformation. And you say, okay, I need a generating function such that, at least to first order in the small parameter, there are no short periodic terms. Let's say, more formally, I want the perturbation to be averaged over one angle or over both angles, the mean longitudes or whatever. Then you want to solve this equation to order epsilon, which means that this H1 plus the Poisson bracket should be equal to this, the Hamiltonian that you want to have at the end. Okay? Now, to solve that, for example, if H1 is a Fourier expansion of this sort, you ask for a similar solution for the generating function. You plug it in, you do the operation, and then you equate term by term to find the coefficients of the generating function, which are these. Okay, I is the imaginary unit. Of course, you will have this product in the denominator, which is an integer vector times the frequency vector, which is rather tricky because it can be the case that it produces a small divisor if you are close to the vicinity of an important resonance, for example. Now, this relation should hold for every k if you want to average over all angles. So to get a Hamiltonian which depends only on the new momentum. And let's say we do that. What is the difference between dropping the terms by hand and using that? The difference actually is that you're defining a new Hamiltonian, which is a function of the new variables. So in principle, even if we use, and I do it too, the same symbols for the variables that we have now, it is not exactly the same variable. If we average using this tool over the mean longitudes, what we get is mean elements, and not the original oscillating elements. So in principle, I should use a different set of symbols, but I will drop the bars just for convenience. Now, I'll do an approximation. I will ask for the generating function so that 2 order epsilon h is independent over the mean longitudes, and the remaining part, which is the second part, I will just take the first few terms, the lowest degree terms that appear in the expansion. Now, I use these modified Delaunay elements, and to simplify a little bit more, I define the pericenter longitude with respect to Jupiter's apsidal line, and also I take the plane of the orbit of Jupiter as the plane of reference and define the mutual inclination. So this kills a few more terms, and the end result is that. You have the Keplerian problem, and you have these terms here. This, I remind you, is roughly proportional to eccentricity squared. This is eccentricity, and this is the first term. It's more or less inclination squared. Okay. There is a term here which appears because I did something that I did not mention. The disturbing function depends on the mean longitude of Jupiter, actually on time, right? So if you want to have it autonomous, you extend the phase space, you define the longitude of Jupiter as frequency times t, and you have to add this term in order for the Hamiltonian to be autonomous. But it's a dummy variable, it will go away essentially. So this is basically Keplerian part plus the lowest degree secular part. Now you will immediately see that the angle zeta is not there. It is ignorable, therefore capital zeta is a constant of the motion. The same holds also for lambda, the semi-major axis, because the mean longitude is not there anymore. Okay? And so the secular part of the Hamiltonian is essentially that one. The rest we can ignore. So we solve now essentially for the evolution of the eccentricity approximation. Well, there is a series of transformations you can do, which is very classical. Let's say you use these Poincare Cartesian variables in order to make the secular Hamiltonian a polynomial, essentially, in these new variables, which is second degree. And then it is easy to see if you take the equation of motion and you set it to 0 that there is a fixed point right there, which means along the direction of the pericenter of Jupiter and at a distance from that origin, which is equal to this. And this is a fraction, because C2 over C1 is smaller than unity. It's a fraction of Jupiter's eccentricity, and we call it forced eccentricity. And if I change the coordinate system, instead of being centered around 0, being centered around this point, this can be done by simple translation, which is canonical, of course, then essentially you drop off the first degree term here. You have this Hamiltonian, and now if I switch back to new polar coordinates around this origin, the Hamiltonian is that. It's the simplest you can get. It's a harmonic oscillator. If I would not do this trick here and I would keep the same terms for the inclination, so I refer to the ecliptic or some other plane, then I would simply add another term for the inclination variable, which I will call now. So you will have two independent harmonic oscillators, and that's it. That's the linear secular theory, essentially, of Lagrange Laplace. Okay? The frequency, of course, by which the new angle conjugate to this capital phi, this small phi, moves is the partial derivative of this with respect to phi, it's C1. And that's the proper frequency of the new variable, which we call the free or the proper, depends on your preference, longitude of pericenter. Okay, that's the variable that goes around here like that. This is for one planet, one perturbed planet. If I want to include more planets in the model, I have first to solve the same problem for the planets themselves, because every planet perturbs the other. And I can do that in the same way, let's say. And the simplest solution that you arrive is this, essentially. The semi-major axis of the planets are constant, and their eccentricity and perihelia are moving like that. Essentially, it's a superposition of different harmonic oscillators. Okay? And these G, J, and Sj are a set of frequencies which are called the fundamental frequencies of the planetary system. Okay, there are different levels of approximation in computing that. In the linear approximation I did, for example, The frequencies are essentially G and S are just opposite to each other when you keep the same index, and one of the S has to be identically 0 because there is an invariant plane that the angular momentum is perpendicular. There are better approximations to do. You can compute more terms, higher order in the mass. If Jacques Lascar was here, he has done this many times. And compute a better approximation of the fundamental frequency of the planetary system, or you could also even do it numerically. Famous work of the Long Stop project 5 years ago? 30 years ago, by Milani, Nobel, and Carpino. And now I plug this solution into the disturbing function for the asteroid, and I do the same trick, and I get a solution for the asteroid, which again gives me semi-major axis being constant, and the eccentricity and inclination motion, related of course to the pericenter of the node, is again a superposition of these terms, which is a sum essentially of forced oscillations by the planet plus a proper mode. Okay? And to this approximation, EP and IP are constants, and they are the linear proper elements for the asteroid. Okay? In principle, these are good, these are nice quantities, they behave nicely. They are constant. You can be used to discriminate orbits and can be used, for example, in the real asteroid distribution to try to identify if orbits that look different are in fact the same. In a sense, they have the same proper elements. Because what I mean is the following. You have a bunch of particles here, and your osculating eccentricity for this particle, or rather the mean eccentricity, is this. And the other particle here has an eccentricity which is this. So they look different if I plot it in osculating element space. But they have the same proper eccentricity, so they are essentially in proper element space, they are right next to each other. So if you look at the distribution of asteroids in osculating elements, you see a blur. You don't know if some of these orbits are actually the same, just in a different phase along the secular evolution. If you plot the proper elements, you see clusters forming that might be what we call asteroid families, which are essentially a bunch of objects that come from collisions of a bigger object and they form a small family. Which over time, because they have slight differences in the beginning in the semi-major axis, they evolve along the secular cycle and they are dispersed in osculating element space. Now, of course, linear proper elements are not that good to do this job. They are not very accurate. We need a better approximation. Also, you should not forget that these M and N here, the amplitudes of the force oscillations, are not so innocent as they appear here, because they have frequency combinations in the denominator that could become near resonant. And these are the linear secular resonances that if you are near there, this approximation of course fails completely. It's the well-known problem. If I have a forced oscillator and I linearize the equation of motion, I get the denominator, and of course you have this result that appears in the books of physics that in a forced oscillation, when you have a resonance, the amplitude becomes infinite. It does not become infinite, of course, but this is an approximation. So in principle, people would like to use higher degree secular theories. To do that, you can do the first step as before, and derive the secular Hamiltonian, but keep a higher degree expansion in the secular variables. Let's say fourth degree in eccentricities and inclinations. Then you can define a new canonical transformation, playing the same trick. You rearrange the terms and keep, for example, everything that is not dependent on the angles in H0, and the rest you put in H1. And you do the transformation with the purpose of killing all the angles and getting a new Hamiltonian that will depend only on the new momenta and therefore will be integral. This is essentially exactly what is being done in the famous paper by Milani and Knežević on the fourth degree proper elements. It's the analytical theory behind it. Don't forget, they did not forget either, to check if some of the terms that you are eliminating to order epsilon will come back at order 2 in epsilon to kill you. For example, when you're averaging out the term related to the 2-to-1 mean motion resonance, and you go back and compute this Poisson bracket, you will see that these terms that you have cancelled multiply in such a way that they give a term which does not depend on the angles, and it's linear in eccentricity. So it has a size μ squared times epsilon, which is an important contribution, at least in the vicinity, but even further out of the 2-to-1 mean-motion resonance.
Emmanuel, sorry,
Yes.
but the normal form is done for a non-resonant motion.
Yes,
right?
yes, yes. So you average. No, I'm talking about the previous step. Sorry, Rosanna. I'm talking about the previous step. So you are in the first step, and you are averaging all the mean longitudes. So you kill the resonant terms to order epsilon, and then you compute this to see if there is any correction introduced in the second term that will be important. And if you do the 2-to-1 terms
If you are not in
combine
the
them,
resonance, but the divisor is small,
yes,
the square of the divisor.
the square of the divisor will give a big enough term. And in fact, it's secular and it's linear in eccentricity.
But you're still outside the resonance.
Yes,
You don't
yes,
do a
yes.
resonant
No,
normal
no,
form.
no, no. You just keep it in order to correct the frequencies enough.
Okay.
Okay?
What happens is that the two models inside and outside the resonance have a singularity in between.
Yes.
So both become wild near the center.
So when you're near the resonance, your frequency that you estimate without this term is much worse than what you would do if you add it.
What about if you do a resonant normal form?
That you would do when you are inside the resonance.
Yes.
Yes.
Or close to
No, no, but yes, or
It
close,
will
but
it will have a singularity when you approach a separated from inside.
no.
Because you have
It's a
zero.
choice in a sense, because if you do it like that, it's supposed to be a more global approximation for the whole belt, apart from the vicinity of the red. Now the thing, this is actually an image from the original paper, if I remember correctly, or the 94 follow-up, with the sample of the known asteroids with good orbits at the time. And these are the proper elements, and you can see clusters that are families, well-known now families of asteroids. And once you have the machine ready, it can be done massively, essentially, as it is being done by the ASTI service. It can also be done numerically in a way, the synthetic proper elements, which means that you do the integrations, you filter out the short periodic terms by digital filtering online, and then you have your mean elements, and then you do spectral decomposition on the time series of the mean elements in order to define the proper frequency with respect also to the planetary frequencies that you know. And it's, of course, very good for identifying asteroid families. It has degraded accuracy near the big mean motion and secular resonances, of course. You cannot avoid that. And the only thing that I should mention is that if you go to very high inclinations, for example, then probably degree 4 is not enough, or you need a lot of extra terms, or you can do the expansion in a very different way, like the theory of Lemaitre and Morbidelli, for example. Now, let me do some secular theory on the satellite problem. This is the potential in which a satellite is moving, and the Hamiltonian can be cast in this form, by which I mean Keplerian part, axisymmetric part that depends only on latitude, the zonal terms, tesseral and sectorial harmonics, and if you want to work on a rotating frame, let's say that we are around the Earth or the Moon and it's rotating, you need to add a term in order to work on this frame. Now, again, if we average over the orbital period of the satellite, essentially, and you want to look at the secular revolution of the orbit, you are left with this set of equations for the 2 degree of freedom problem. I showed you yesterday the J2 result, and now let's say that we add only one extra term, the J3, which is still axisymmetric. The J2 is a Hamiltonian that depends on no angle, so all the momenta are constant. Here you add one extra term, and you include one angle, essentially, the pericenter. Okay, the argument pericenter. It's still an integrable Hamiltonian, of course, because it's 1 degree of freedom. And the equations of motion give you this, which is a well-known result to some approximation in eccentricity and inclination. And on the other hand, I is not a constant, this is a mistake, H is a constant, but that's okay. H is a constant, and this system has some interesting fixed points, because this can be 0, of course, at the critical inclination, but also can be 0 when this is 0, so G is plus or minus P over 2, and this is 0, which is this function here, and it can be satisfied for some small value of the eccentricity in different inclinations. These are the so-called frozen orbits. And of course, if you're not satisfied with how well you approximate the frozen orbits in this third-degree model, you can do much better. For example, in a paper by Kleomenis and Milani, they average the whole perturbation over H, over the node, which anyway seems to be unimportant, at least to third order, and they keep all the zonal terms up to some degree, in which case you are still in a 1 degree of freedom problem, but you can compute a much better approximation of the position of the frozen orbit. In case you are interested in working on the full 2 degrees of freedom problem, which may be needed in some bodies at least, and you work on a general, on a complex gravity model of the secular Hamiltonian, in order to follow the dynamics, you can use, of course, different other tools. One way is to do some sort of frequency analysis. I don't know if Jacques Lascar is going to speak about it when he comes, in order to get a global view of the dynamics. As we saw, when you introduce the J3 term, essentially you have a problem with one important frequency, the proper mode of the barycenter. So you can map different orbits with different initial inclinations and eccentricity on a frequency map. This is the value of the proper frequency, or the amplitude map, the proper element, let's call it, of the orbit. Now, what is this experiment? This is a 7-degree model with all harmonics, secular, for the moon. And you place an orbit at an altitude of 200 kilometers, semi-major axis 200 kilometers plus the radius of the moon. And computing a few thousand orbits here. The white regions are empty because the orbits collided within a time which is less than a few months, let's say 8 months, I think, was the limit here. And why do they collide? Well, they're not chaotic orbits, they are regular orbits for the most part, but the oscillation induced because you are librating around the frozen orbit is big enough to make the barycenter fall below the surface of the moon. So they collide. The rest remained there for 8 to 10 months, and the frequency value is color-coded here. The hatched part is negative, just showing that after the critical inclination, the sign of the secular motion changes. That we know. On the amplitude map, you can see that where it's darkest, you have the minimum eccentricity variation. And the dark bands here and here follow exactly the positions of the frozen orbits of this model, okay, in the 7-degree approximation. Here you see also some stable periodic orbits, but please pay attention to the fact that they have a different symbol because they are on the opposite side of the apsidal line. Okay, so I'm just putting everything on the same plot. So there you have the stable periodic orbits with minimum eccentricity variation, while here you have maximum eccentricity variations because the stable periodic orbit is on the other side. This is a tool you can use easily, and for example, what we did, we took different models of different complexity and we applied that, and we set a criterion for when the frequencies or the amplitudes don't change much from one model to the other, in order to identify, let's say, the simplest possible model that would capture the dynamics of the 2 degrees of freedom system with good accuracy. So for the moon, for example, a model that contains J2, J3, and J7 is, for some reason, is a good approximation in the axisymmetric case. If you want to have more information in the 2 degrees of freedom, you need to add also the C22 and C31 terms of the moon lunar potential. Now, if you have an orbit which is near the frozen solution but not quite in the frozen solution, you can see immediately that doesn't stay there. This is a projection of the E cosine G, E sine G plane. The initial condition is somewhere here, and the black curve is an orbit that it actually has a shape like that, the red one, which moves in this direction around some center. So it's drifting, let's say, in eccentricity, and if it goes far away from the frozen solution, it can collide on the surface of the moon. If I take this orbit and I do a decomposition, spectral decomposition of the time series, I will find out that it is as if there is a center of motion here, a long libration period, which gives me this drift, and this is the short periodic part. The question is, knowing that, whether we can do better, whether we can find a better orbit that will stay closer to what we know as the frozen solution. Remember, it's a 2 degrees of freedom problem, so in fact, there doesn't exist a frozen solution. There exists a periodic orbit, which is on this section at a given value of the nodal longitude would be a point, like the frozen solution. So actually what we do is we take this decomposition and we filter out the blue term, the libration around the frozen solution. And in this new filtered solution, we set t equals 0 and we get a new initial condition. Then we integrate the new orbit and we do the decomposition again. And we filter out the slow term and we take a new initial condition. And you can do that iteratively. If you do 3 iterations, then from the initial black orbit, which has this libration cycle overimposed on the short-term period, you get the new initial condition and you do the spectral decomposition and you find this violet curve now as the slow mode. And you do another iteration and you find this red circle as the new long periodic term. In practice, from the black orbit here, you do one iteration, you move to the blue orbit here, you do another iteration, you move to the red orbit here, which is almost exactly the periodic orbit that exists there. And you can find by 3 iterations of this filtering method. Okay? This is actually very efficient, and you can compute, for example, for every inclination, the periodic orbits that are in the position of the frozen orbits of the axisymmetric problem. And in fact, it gives you exactly the same results as differential corrections. Okay? And to illustrate why we like it so much, let's say I have an orbit. I compute the frozen solution or the periodic orbit for a model of the moon that is up to degree 10 in all the gravitational parameters. Okay? Degree and order 10 model. It would be stable, it would behave like that in this 10-degree model. Now, if I take these initial conditions to use it as a first guess solution for a gravitational model of degree 20, and I integrate, it doesn't stay there. It's the black curve which collides at some point to the surface of the moon if my altitude is, let's say, 60 kilometers. However, I can take this solution that collides, iterate the filtering method 2 times, and reach the red orbit, which is the correct periodic orbit of the 20-degree model, and will stay there, will not collide, or rather I should say, if there is a circular orbit at this 60 kilometers that does not collide with the surface of the moon, it's that one. Okay, so you can find the optimal orbit by applying this iterative scheme of filtering, and without being able to prove it, it converges at all inclinations. I don't know why. It converges at all inclinations very fast with 3 iterations, and it works. Okay. So I think, I don't know, Alessandro, if you want, I don't know how much time I have left. We can take a break now, we can have questions now, and we can start with.
Well, theoretically you have still 10-15 minutes, but if you think it's a good point to break.
It depends on you, because I'm finished with what I wanted to say about secular theories, and I wanted to move to the resonant problem. We can either take questions and short break now, and then, okay?
Okay, let's make a short break.
So I'll stop here before going to the mean motion resonant problem.
Okay, if somebody has question on this.
Please.
Yes, please.
I have one question that comes back to the comment that was made before. I don't know if I understand it correctly, so I just want to confirm the understanding. That you treat the resonant regime completely separately from whether it's linear or higher order secular theory for, let's say, the distant.
Yes. The idea is I want a secular theory, which I know will not be good enough in the vicinity of resonance. But I want at least my frequencies to be close to the real frequencies in the full problem. Meaning, if there is an important resonant nearby and gives, let's say, a long-range effect, it will not completely kill my normal form when I'm away, but it will give me some perturbation that I need to include. Okay? So, in principle, I keep the first-order terms up to the degree in the expansion that I want, but I keep an eye on the second-degree terms to see if some of them is big enough and could give me a correction that is meaningful, because, like I said, the first term that I will keep in my expansion would give me some frequency. The 2-to-1 resonance by itself alone, if I do the combination to second degree, will give me a term which is linear in the action, so it gives a correction to the frequency. I need to know how big is this correction. I cannot ignore it beforehand.
So the third scenario, I guess that I'm wondering which one covers that, or if that's separate. Because in the case of the close encounters,
No.
that falls
No.
completely outside the scope.
That's completely outside. Secular theory assumes essentially that the bodies are well separated. We have no close approaches. Well, any expansion will diverge anyway.
So for the main belt, for instance, if you're trying to model that over a long enough period where you expect close encounters to occur, then you would have to deviate from.
Well, in principle, for the main belt, if you find proper elements that are stable for tens of billions of years, then you can be confident that the timescale on which you might have escaped from the main belt to become an NEA is billions of years, so you don't need it. Okay?
Yes.
Yeah, this plot shows the dynamics of the eccentricity.
Mhm.
And did you also do the analysis? So you found like the optimal orbit
Mhm.
in the eccentricity phase space, but did you also analyze if what happens to the inclination? for
Yes,
the-
yes. As expected, because I told you before that the terms that give you change in the inclination are very small compared to the other ones. You have, of course, variation in the inclination, but it's very small. So, for example, this is an orbit, this is a polar orbit, and the variation in the inclination is about a degree. Okay, this is near polar orbit, it's 98 degrees, inclination slightly retrograde, and the variation is again of the orbit of the order of 1 degree, no more. Okay, but the point that I'm striking is that the red one is a periodic orbit of the system. There's no drift. I cannot control these variations, which are short term, depend on the motion of the node. Give this slight variation in the inclination and give me some variation of order 10 to minus 3 in the eccentricity. This I have no control. What I can control is the initial condition in the sense of killing by this iterative method the slow mode that goes around the frozen orbit, so bringing it essentially about the correct center of the motion. So this term is completely killed. So if there is an orbit that does not drift in eccentricity and does not have any probability of colliding, it's this one. The thing is that you can do the following, because actually it converges even if you start far away from the real solution, because it's essentially one mode. All the curves are librating or circulating around the frozen orbit, right? More or less. So even if you start far away, you converge on this. So I can do the following. I have an analytical formula to calculate where are the frozen orbits in the simple axisymmetric third degree problem. Okay? But I can give you the numbers immediately. I can use that as an initial guess, plug it in a model of the moon, which is, I don't know, where am I? Sorry. Plug it in a model of the moon of degree 30, whatever. And of course I will get an orbit that doesn't stay there, it starts drifting and maybe colliding. I only need to integrate for a few months, let's say 4 or 5 months, then take the Fourier decomposition. Well, it's actually, we don't use a Fourier decomposition, but that's another story. Take a frequency decomposition, see the slow mode, kill it, get a new initial condition, repeat that 3 times. Then you arrive at this one, which has no slow libration around the periodic orbit that in these 2 degrees of freedom model replaces the frozen.
So, but now this is applicable to an order of degree, to a model of degree in order 20.
We have checked 7, 10, 12, 14, 20.
Oh,
Just
okay.
didn't bother going to higher.
But-
In principle, it does not depend on the model, as
Okay.
long as we know from the previous work that beyond order 7, the variations of the frequencies and the amplitudes are meaningless. Of course, they are important for a specific orbit and specific altitude and so on, and you need to work it well. But as long as you know that beyond a certain approximation, the differences are minimal, it doesn't matter which approximation you do. If you have the full model, you can use the full model. Okay?
Yeah, thanks.
And how robust are these orbits? For
Sorry?
example, how robust are these orbits with respect, for example, to non-gravitational solar radiation pressure? I mean,
I haven't checked because also these are circular orbits. Remember, I don't have the mean
okay.
motion. The correct way now to complete the machinery would be that if I have this solution, so I have the initial conditions in terms of these mean variables, mean elements, then I would go back to this, to the Lie series, and compute the Lie series of the old variable with respect to the new variable. So I would say old variable equals the Lie series of the new variable. So I plug in the initial conditions that I found of the circular orbit and get back some values for the initial oscillating elements to use in a full model now without any approximation to see how robust the orbit is.
Yeah. Do we want?
Which I would not be able to do if I would just throw away the mean longitude terms
Sure.
and
Sure.
work in the mean elements directly, because I don't know the relationship between them.
I don't know. Do you feel like having 2 or 3 minutes break?
Sure,
Just to-
short break.
Okay, very short break.